So the next thing we're going to look at in regards to sampling distributions has to do with some different things involving quantitative data, which involves what are known as sample means. So some things here first, and sample means, when we're talking about quantitative data, what we have and what we're going to look at are some different things with the mean, which is represented with mu, and then we also have the standard deviation, which we're going to represent as sigma. We got mu x, sigma x here. So those are the different notations that we're going to use when we start to talk about this is for the population mean. This is for the population standard deviation. And then what we have here for the sample mean, which is sort of what gets mentioned here, is x bar. This is the sample mean. So when we're talking about a sampling distribution involving quantitative data, one of the things that we're going to look at is the shape, the center, and the spread, just like we did when we were talking about categorical data. So what you have here on the left-hand side is the population distribution based on household earnings versus the percent of households. And if you notice here, you have a graph that's skewed to the right. So we would say that this graph here is skewed right. But if you notice that if I were to sample of size 100 from this population that appears to be skewed right, of a size 100, I get a sampling distribution that is pretty normal looking. It's roughly symmetric. So one of the things that we are going to investigate is the relationship between, as far as shape goes, the relationship between the population distribution and the sampling distribution that goes with it. So as far as just some formulas go, whoops, too fast there. Okay, the sample mean, if we're talking about a sampling distribution, the sample mean is simply just the value of the population mean. However, the standard deviation of the sampling distribution, we can find that value by dividing the population standard deviation over the square root of the sample size, as long as the 10% condition is met. So just as we talked previously about how the 10% condition needs to be met when we were talking about categorical data, the same is true for when we're talking about quantitative data. So just point of note here at the bottom, these two facts, the mean and the standard deviation for x bar, are true no matter what shape the population distribution has. And that's one of the things that we're going to look at in terms of the shape of the sampling distribution as a function of the population distribution. So here's just a simple normal curve where we have the population mean down the middle, there's mu, and then once again we're going to break up the curve with the values of the standard deviation, which we'll find by doing the population standard deviation over the square root of the sample size. So a quick example here says, suppose that the number of movies viewed last year by high school students has an average of 19.3 with a standard deviation of 5.8. Suppose we take a simple random sample of 100 high school students and calculate the mean number of movies viewed by the members of the sample. What is the mean of the sampling distribution? Well, if the average in the population is 19.3 movies, then we would say that the mean of the sampling distribution would also be 19.3, meaning that if we were to sample from this population over and over and over again, we would expect the results to be, or the center of the graph to be, somewhere around 19.3. Question number 2, what is the standard deviation of the sampling distribution? Check that the 10% condition is met. So if we're sampling 100 high school students, the standard deviation for this I would find by taking the population standard deviation divided by the square root of the sample size, and that comes out to be about roughly 1.58. And then as far as the 10% condition goes, if there's 100 students in our sample, then what we would need to assume is we would need to assume that there's at least 1,000 high school students in the population, which in fact is true. So some different things involving the normal condition with sampling distribution. So this right here, very important piece of information in regards to shape. So there is this here, if the population distribution is normal, then so is the sampling distribution. So regardless of the sample size, if you know that your population distribution is normal, then you can assume that the sampling distribution, regardless of size, and that's what this says here, there is This is true no matter what the sample size is. If your population distribution is normal, so will your sampling distribution, regardless of what the size is. And then just remember, when we're talking about standard deviation, just remember to check your 10% condition before you calculate that value there. So that's basically what this is kind of mentioning at the bottom here. So an example involving the normal condition with quantitative data and sampling distributions is this. It says the height of young women follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is 66.5 inches tall. So in this case, we're only randomly selecting one person. Our sample size here would be n equals 1. So when I go to do this, so first what I want to find is what the z-score for 66.5 inches would be. So in this case, I'm going to do 66.5 minus 64.5 divided by 2.5, which comes out to be 0.8. And then if I do the normal CDF from 0.8 to E99, here's the probability, 0.2119. So that would tell me I got roughly about a 21% chance of choosing somebody who's taller than 66.5 inches. The second part of this says find the probability that the mean height of a simple random sample of 10 young women, so in this case n would equal 10, exceeds 66.5 inches. Now because I'm sampling 10 young women, that's going to change the value of the standard deviation here a little bit, because now my sample size isn't just 1 anymore. So for a simple random sample of 10 young women, the mean would stay the same. However, the standard deviation, I would need to do this in order to find it for the sample of 10. So I would say the population standard deviation divided by the square root of the sample size, and that comes out to be roughly 0.79. And then from here, I can now do the z-score for 66.5 inches. And when I do that, I get a z-score of 2.53, and then if I do the normal CDF of 2.53 to E99, I get a value of 0.0057, which basically means I don't have a very good chance. This number here is less than 1%. I got a less than a 1% chance that you would find that we would choose a simple random sample of 10 young women whose average height exceeds 66.5 inches. So that's just a very good example of some different things involving the normal condition with sampling distributions and sample means. So in terms of the this question here, once again, we have the mean and the standard deviation for this. And if you take a look at this here, what it gives you is the differences between the population distribution and the sampling distribution. So not that this is something that you're going to have to be able to draw on your own, but just to give you an illustration of, a comparison between the population distribution versus the sampling distribution and how they relate to each other on the normal curve. So different question here, similar to the one we just did. It says the length of human pregnancies from conception to birth varies according to a distribution that is approximately normal, with a mean of 266 days and a standard deviation of 16 days. So just note that it mentioned the population distribution here was normal. It says find the probability that a randomly chosen pregnant woman, so that would be n equals 1, has a pregnancy that lasts more than 270 days. So in order to do that, I want to know what the z-score is for 270 days. So I'm going to do 270 minus the mean, 266, divided by the standard deviation. And when I do that, I get a z-score of 0.25. And if I do the normal CDF from 0.25 to E99, that's the value that I get there, 0.4013. The second part of this says, suppose we choose a simple random sample of 6 pregnant women. So for this one, I would have n equals 6. What is the mean of the sampling distribution of X bar? So remember that regardless of what your sample size is, the mean will always stay the same. So if the population mean is 266, then the mean of the sampling distribution will also be 266. For question number 3, compute the standard deviation of the sampling distribution, remembering once again that n equals 6 here. Check that the 10% condition is met. So for this one, to check the 10% condition, if I'm sampling 6 pregnant women, then I need to assume that there is at least 60 pregnant women in the population. Very true. Therefore, the standard deviation for this I would find by doing the population standard deviation, which is 16, divided by the square root of the sample size, which comes out to be roughly 6.532 days. So to find the probability that the mean length for the women, the mean pregnancy length for the women exceeds 270 days, now, and this is for, once again, when n equals 6. So I'm going to do the z-score for those, which would be 270 minus 266 divided by this standard deviation that I got from here, 6.532, which gets a z-score of 0.61, and then if I do the normal CDF from 0.61 to E99, I get a probability of 0.2709. So once again, just some different things involved with sample means and the sampling distribution with the normal curve. So keep in mind that when the population distribution is normal, we can assume that our sampling distribution is normal. But what if either A, we don't know what the population distribution is, or if we know that the population distribution is not normal? What does that mean in regards to our sampling distributions? So that's where this whole business of what's known as the central limit theorem comes in. So with the central limit theorem, and just take a look at some different things here, what we know is that regardless of what the population distribution shape is, whether it's known or whether it's some sort of shape other than normal, what we do know is that regardless of the shape, if we take a big enough of a sample size from the population, then we know that as the sample size increases, that the more normal looking that the sampling distribution will be. So the question that comes up here with this is, how big of a sample do you need to take in order to be sure that your sampling distribution is in fact normal? So here's just some different things here. So this right here is a population distribution from a Rice University sampling applet. So this is the population distribution that comes from that. And then what we did here was we sampled from that population, and we took a sampling distribution from this original population here. So you guys can see here, this graph, you have some gaps in here. It looks like, you got a graph that looks like it's kind of skewed left here. This one is roughly symmetric kind of here, and then you got another piece to it over here that's skewed to the right. So this population distribution in terms of its shape is all over the place. So there isn't really any sort of discernible shape that's involved with this population distribution. However, what you're going to notice here is that as we increase the sample size, so A here, we did a sampling distribution where the sample size was 2. For B, we did a sampling distribution where the sample size was 5. For C, we did a sampling distribution where the sample size was 10. And then for D, we did a sampling distribution where the sample size was 25. And over here it says, describe the shape of the sampling distributions as n increases. What do you notice? Well, hopefully from this you notice that as you increase the sample size, as you go down here, these graphs start to look much more normal. So in other words, if we're talking about a sampling distribution in terms of its shape where either the population distribution is unknown or we know that the population distribution is not normal, what we can assume is that the sampling distribution would be normal or would be approximately normal as long as the sample size is 30 or more. So that's the magic number that we're going to use in regards to sampling distributions and determining whether those sampling distributions are normal if in fact we either A, do not know what the shape of the population distribution is, or if we know that the shape of the population distribution is not normal. So just to kind of use an example of some different things involving the central limit theorem, and it says here, based on service records from the past year, the time that a technician requires to complete preventative maintenance on an air conditioner follows a distribution that is strongly skewed right and whose most likely outcomes are close to 0. The mean time is 1 hour and the standard deviation is equal to 1. Your company will service a simple random sample of 70 air conditioners. You have budgeted 1.1 hours per unit. Will this be enough time? So as far as some different things with being able to answer this question, the first thing I guess would be this, and I'm talking about the 10% condition. So what we would need to assume is if we're going to take a simple random sample of 70 air conditioners, we would need to assume that there's at least 700 air conditioners in the population. So the sampling distribution for the mean on the 70 units would be the same as the population, the mean of the population distribution, which in this case would be 1. And then the standard deviation for the 70 air conditioners would be the population standard deviation divided by the square root of the sample size, which comes out to be roughly 0.12. So as far as the normal condition, now notice it said in the population distribution that it was strongly skewed right. However, because the sample size for this is 30 or more, in this case it's 70, I can assume, because that sample size is so big, that the sampling distribution will be normal. So what that allows me to now do is to be able to answer this question. So we need to find what the z-score would be for 1.1 hours. So when I do that, I get a z-score of 0.83, so that's 1.1 minus 1 divided by 0.12. And then now I want to do the normal CDF for 0.83 to E99, and when I do that, I get a probability of 0.2033. So in other words, what we're basically saying here is that if you budgeted 1.1 hours per unit, then there's a 20% chance that technicians will not complete the work within the budgeted time. So that's just some different things there with the central limit theorem, with the normal condition, and some different things with sample means. So last question here, and it says, suppose that the number of texts sent during a typical day by a randomly selected high school student follows a right skewed distribution with a mean of 15 and a standard deviation of 35. Assuming that the students at your school are typical texters, how likely is it that the random sample of 50 students will have sent more than 1,000 texts in the last 24 hours? So to answer this, what I need to know, or what I'm looking for, is what's the probability that one student will average, in this case, 20 or more texts. So if we know that 1,000 texts were sent by 50 students, then that means on average 20 texts per student were in fact sent. So what I want to know here is what's the probability that the average student sends 20 or more text messages. So in terms of the conditions here, once again, I'm looking at the normal condition with the central limit theorem. So since the sample size is more than 30, we can assume that the sampling distribution would be approximately normal. So with the standard deviation here, I want to check the 10% condition. So since my sample included 50 high school students, I need to assume that there's at least 500 high school students in the population. So since that's a safe assumption, I can now compute the standard deviation, which would be 35 divided by the square root of 50, which comes out to be 4.95. So for this, I can now compute the z-score for the 20 texts per student. So this would be 20 minus 35 divided by 4.95, and I get a z-score of negative 3.03. So I want to know what's the probability that z would be greater than negative 3.03. So if I did the normal CDF from negative 3.03 to E99, I would get a value that was 0.1562, which in this case means there's about a 16% chance that a random sample of 50 high school students will send more than 1,000 texts in one day. So to finish up with one other thing here, and this just has to do with some different things with comparing probabilities. So the question here says the heights of students at Interboro High School are normally distributed with a mean of 68 inches and a standard deviation of 5 inches. So since it mentions that the population distribution here is normal, I can now just assume, regardless of sample size, that the sampling distribution or the shape of the sampling distribution will be normal. And question number 1 says a single student, so in this case we're going to say if n equals 1, is selected at random from the high school, what is the probability they are taller than 71 inches? So in order to answer this, first I got to check the 10% condition. So if I'm sampling one student, right, I would need to assume that there's at least 10 students in the population. Safe assumption there. So the mean for this would be 68 inches, just like it was from the population. The standard deviation would be 5. So to do the z-score for this, I would do 71 minus 68 divided by 5, which comes out to be 0.6. And then I take the normal CDF from 0.6 to E99, and that comes out to be roughly 0.2743. So that's question number 1 there. Question number 2, I'm going to change the sample size, and now I'm going to make it, instead of n equals 1, I'm going to make it n equals 3. And I'm going to do the same thing here. So notice that the mean will stay the same. However, the standard deviation is going to be a little bit different because now my sample size is no longer 1. So when I do this, I'm going to take the population standard deviation divided by the square root of the sample size. So when I get the z-score for this, it comes out to be roughly 1.04. And if I do the normal CDF from 1.04 to E99, this comes out to be roughly 0.1493. And then for number 3, if I take the two questions here, explain why the probabilities in 1 and 2 are not equal. Well, simply put here, they're not equal because the sample sizes are different. So because the sample sizes are different, my standard deviations are going to be different, and then once your standard deviations are different, that changes your z-score, which obviously then changes your the probability that would occur. So just some points of note here in the summary. One obviously is the formula that we're using for the standard deviation for a sampling distribution involving quantitative data. Also remember, with your normal condition with that. And then the other thing is this whole central limit theorem, okay, where we can assume that the sampling distribution is normal if we know that the sample size that we're using is 30 or more.